Hi everyone, let's take a look at a question on AP and GP. So in this question, we are given the sum Sn of the first n terms of a sequence, and the formula is given to be Sn equal to minus 2n squared plus an. So let's write it down first, minus 2n squared plus an. And part 1 of the question wants us to find an expression of un in terms of n and a. So for linking of a formula between a un and an Sn, we got this formula here, which is un equal to Sn minus 1. So just to take note that this formula can also be applied to any kind of series. It's not only restricted for AP and GP. So we will have a un equal to Sn will just be this, minus 2n squared plus an. Minus away Sn minus 1. I will just replace all the n away with n minus 1 here. So I will just get minus 2n minus 1 squared plus an minus 1. I think all that is left to do is just to expand out this particular expression and just to simplify it, and we will be able to get our un. So let's do it now. So minus 2n squared plus an. Let's multiply this minus in first, so plus 2. This one we can expand and square, minus 2n plus 1. So multiply this minus in, I'll get a minus. This, I'll just leave it first. Okay, so next step, minus 2n squared plus an plus 2n squared minus 4n plus 2 minus an plus a. Okay, so this one will be cancel away. So this one cancel away, this one cancel away. So I will just left with minus 4n plus 2 plus a. Okay, so this will be my answer for my part 1. And part 2 says, hence determine if the sequence is a arithmetic progression. So to show whether is it AP progression or not, we will be using un minus 1. So what we are doing here, we are using a general term for this series, and you will be subtracted by its preceding term. So as long as you will be able to show that it's a constant, then it will be an AP series. In fact, actually, you can also use un plus 1 minus un. It will be the same because, in fact, you are just using this general term minus away its preceding term. Okay, so let's sub in what is our un and un minus 1. So un will just be this, minus 4n plus 2 plus a. So minus away un minus 1, replace all the n I see with n minus 1. So I get minus 4n minus 1 plus 2 plus a. Alright, so our objective here is to try to simplify it and make sure you only left with a constant. That means to say, have to make sure this entire expression left over should be independent of n. So I will get minus 4n plus 2 plus a, multiply the minus in, plus 4n minus 1, minus 2 minus a. Okay, I can see the a can be cancelled away. The 2 can also be cancelled away. So, and I expand this, I'll get minus 4n plus 4n minus 4. So these 2 will be cancelled away. So I'll left with minus 4. So that's very good because it will just be a constant minus 4. In fact, this minus 4 is a common difference of this series. So we can just do our conclusion. Therefore, un will be an arithmetic progression. Okay. So that will be my part 2 of this question. So for part 3, it says describe how the sequence of sums That means our Sn will behave when A is equal to 20. So looking at this expression, I'll just replace this A with 20 first. Let me just erase this part. So in the end, I will end up with Sn equal to minus 2n squared plus 20n. Alright, I think what we can do, in fact, we can just make use of a GC to see how the sequence will behave. Right, so for this, I've keyed the equation already. Minus 2x squared plus 20x. So I'll just replace all the n with x here. So what we are going to do, right, I will be using the table to generate the different values for different values of n. I don't really need to use the graph because I know that this n actually is an integer. So when we are looking at integers, right, it will be clearer if we just make use of the table. So from here, I'll just go to second graph. Okay, so this GC will generate all the values of different n's, like when it's n equal to 1, you sub in, you get 18, and so on and so on. So what we are going to do is to observe how this series will behave. So I can see that initially it will increases until 50. After 50, then you can see that it will start to decrease. And I think probably it will continue to decrease until minus infinity. All right. If you want to, just to be sure, you can go to second window. Maybe I can just put a value of 50 and see what happens. Maybe we can try not to put in a very large number, because sometimes if you put in a very large number, the GC will take an awful long time to generate the values out. All right, that's right. So our initial suspicions is correct. So how we're going to describe it, right? Probably I'll just describe it as from GC, the sequence will initially increases to 50. Then it will decreases indefinitely to negative infinity. Right, this will be my description for the series. So part B says you are given a GP with first term of 7. Let me just write down all the info first. So first term is 7, common ratio is R, is an unknown. Common ratio is R. And the sum of the first 15 terms of the progression is 28. So I know that S15 equal to 28. And part 1, you are supposed to show this particular equation. Okay, then after that, explain why the common ratio cannot be 1. Okay, let's make use of the formula for the GP first. So for sum to 15 term, the formula is A bracket 1 minus R to the power of 15 over 1 minus R equal to 28. Sum in the values, so 7, 1 minus R to the power of 15 over 1 minus R equal to 28. Okay, maybe I can just simplify a bit first, 7. So this one I will left with 4. Multiply this over to the other side. 1 minus R to the power of 15 equal to 4 minus 4R. So R to the power of 15 will just be equal to, maybe I can just shift everything here. So I get minus 4R plus 3 equal to 0, which is short. Okay, so how can we explain why the common ratio cannot be 1? I think for a GP, right, common ratio can never be 1. Because if the common ratio is 1, that means to say your entire series will just simply be a constant value, right? So how am I going to explain? Maybe I can just write ratio common ratio cannot be equal to 1. Since for a GP, all the terms cannot be the same. Alright, basically I can just explain it something like this. It's just like for a AP series, right, the common difference cannot be 0, right? If the common difference is 0, so all the different terms are all the same, then it's not AP. So in this case, if the common ratio is 1, then it will not be a GP. Okay, so for part 2, it says given that your common ratio lies between -1 and 1, and you're supposed to find the sum to infinity. So perhaps actually we got to make use of a GC to solve the roots for this one. Right, so from here, I've keyed in the equation ready. So that is the second equation here. So what we're going to do is we are going to graph this now. So when I graph this, I will get a graph that probably shows that we will have 3 roots. So we have one of the roots here, one root here, and the other root here. So we can make use of the function, the 0 function, or we can use the intersect function to find out the values for the common ratio. So just by using GC, right, from GC, I should be able to determine the values of R, and it will give me 3 values. So one of the values is -1.44, -1.1445. This one is rejected because our common ratio should lie between -1 and 1. So this one is rejected. The other one is R equal to 1, so also rejected because of this. And finally, our last roots we have for our common ratio is 0.75359. Okay, this is the common ratio I want to use to find my sum to infinity. I will just leave my answer to 5SF. Okay, so therefore, sum to infinity, the formula is A over 1 minus R. So our first term is 7. The common ratio is given by this, 0.75359. And working this out, I will be able to get my answer as 28.41 to 2 dp, since the question 1 asked to leave our answer to 2 decimal places.